Okay, so we kind of separate this into two videos. We talked about the prisoner's dilemma last time, but I want to do a couple more examples of it, just to kind of put some, I don't know, think of how we would kind of model different scenarios and how we can kind of put them into these payoff matrices. So let's say I've got, sorry, I'm moving some things around. I've got two candidates, right? This is kind of a relevant example. I've got a Republican and Democrat. And I'm thinking about, around election season, you see all these negative ad campaigns. So if one of the candidates runs a negative ad campaign, that's going to hurt the other candidate. So if the Republican runs them, the Democrat loses votes. Maybe the Republican, doesn't gain any, right? Maybe they can, or maybe they do. Maybe they gain 1,000, right? But everybody who they lost here, so like maybe I convinced 1,000 people to switch from voting Democrat to the Republican candidate, but the other 2,000 don't vote. And then here, if the Democrat runs the negative ads, well, the Republican loses 3,000, the Democrat gains 1,000, but 2,000 people say, there's no candidate I want to vote for. So if they both refrain from running attack ads, right, nothing changes, right? People are going to vote for who they're going to vote for. So we could kind of model this, right, as a normal form game. And so I think I have my animations turned off here, but we'll kind of walk through them. So if we both don't run attack ads, nobody gains or loses any votes from attack ads, right? They're not being run. So the kind of gain to both people will be essentially 0 here. Now, if I'm the one that runs the attack ads, I'm going to gain 1,000 votes and the other person loses 3,000. So if I run the attack ads as the Democrat, I gain 1,000. The other person, the Republican candidate, loses 3,000. Now, if we both run attack ads, the gain and the votes kind of offset each other. And we both basically just convince people that there's no good candidate and 2,000 fewer people vote for each candidate here. Well, this is a perfect example of a prisoner's dilemma because here, and I shouldn't say it's a prisoner's dilemma because kind of for the Republican and the Democrat, they don't care, but it's a prisoner's dilemma for society. So if the other candidate does not run attack ads and I don't, I gain no votes. But if I do, I get 1,000. So that's going to be my best response. If the Republican runs attack ads, what should the Democrat do? Well, if they don't play that game, they're going to lose 3,000 votes. Whereas if they also run attack ads, they're only going to lose 2,000. Same kind of incentives exist. I kept these payoff symmetric. So if the Democrat runs attack ads, the Republican, if they don't run attack ads, they don't gain or lose any votes. But if they do run some, they can gain 1,000. And then if the other candidate, the Democratic candidate, runs attack ads, if I don't, as the Republican candidate, I lose 3,000. But if I also run attack ads, I'm only going to lose 2. Well, notice here, what do the candidates care about? They don't care necessarily about the number of votes. They care if they get more votes than the other person. So in a weird way here, we can solve this model and we end up with this Nash equilibrium where both individuals run these attack ads. Now, for the candidates themselves, I mean, even if I tie, I'd like to have more votes. But here, if no votes are gained or lost for both candidates, and here they both lose 2,000, the results aren't going to change, right? But who loses out here? Well, society, we now have a lot of people not voting. We would kind of say that's a negative for society. So this is kind of an example of our prisoner's dilemma. It's a little bit of a weird one, but I always kind of like it. I think it's kind of a fun one, kind of relevant to the time. So, here we've got really, there's no impact on the election from these attack ads. If we're both running them, we're just convincing people that both of us are terrible people and that no one's going to, and we're just going to see people not vote, right? This was the idea that 4,000 people now will not be voting, right? And that would be a negative result for society. So game theory can help us understand some of these issues. So some of the other examples we see of prisoner's dilemma, ad wars, it's the same idea as like the negative ad campaigns. It's always better to be the firm that spends a little bit more on advertising, right? It's always better to be the company that shows up in an advertisement on the Super Bowl when the others aren't. So what happens, all of these firms start dumping lots of money into ad campaigns. Well, if we're all running ad campaigns, it all offsets each other. We haven't gained any additional revenue or customers. We've just spent more money, so we've decreased our profits. So if we could somehow both agree, hey, we're not going to run any ads if you don't. Okay, well, now we don't have these huge costs. We still have the same customers we did before because no one's been convinced to like buy from the other firm. So we could both be better off. So another good example of a prisoner's dilemma. anytime we have like these cartels where they try to coordinate their quantity or price decisions, we looked at some models in the previous video of that. It can result in that it's best to be the one that breaks it. So that's kind of good in the sense that there's always an incentive that pushes firms to break these agreements to act like a monopolist and pushes us closer to that perfectly competitive equilibrium. Another good example is arms race, right, between military. It's always better to be the country that spends more on your military, right? There's a dominant strategy of that, right? So what ends up happening, all these countries spend lots of money on their military. Well, is that a good thing? Well, I mean, if we could somehow agree not to attack each other, that would make everybody better off because now we're not attacking each other and we haven't spent all of this money on our military. Common resources, another kind of, we can model those as in a game theoretical way. So this is the idea that like if I use the resource, but no one else does, I'm better off, right? But everybody has that incentive to be the one that uses the resource. So if we don't fish this lake, well, then we have kind of fish there, or if we only, let's use deer since it's kind of deer season. If I only use the number of allotted deer tags that the government gives me, I only, I forget what it is in Indiana. I think you can kill a buck and a doe, maybe. I think it's two. If it's not, I apologize. I get mixed up with Michigan and Indiana. They change year to year, I think. So if we all only kill kind of our allotted 2 deer, well, then this common resource can repopulate. But there's always an incentive. Well, I'd like to have a little more deer meat. So if I kill a third one and don't report it, I'm better off, right? But if everybody has that incentive, we end up with this combination of strategies where everybody's hunting more than their allotted 2 deer, and we drive that population down to extinction. Now we're in an outcome. Now nobody's getting any deer. It would have been better if we could have agreed to both kind of hunt a lower number, right? So just a couple more examples of the prisoner's dilemma to kind of round out that discussion. With this idea in mind, we also talked about, and I kind of mentioned it with the cartels, that as long as we have an incentives that for both firms, it's better for them to break the agreement, which generally is going to push us closer to that perfectly competitive market, right? So we don't have to be as concerned about companies colluding or working together. However, right, just because in all these models, we're kind of thinking about like it's a single point in time. They're making the decision about how much to produce or what price to set today, right? So what can happen, even though we have this prisoner's dilemma in the arms race, common resources, all these other things, why doesn't it always break down? Why don't we see, every single type of, the deer population, why doesn't it get overhunted? Why doesn't every single pond have 0 fish? Why does, some firms really are able to act like cartels or monopolies? So why would sometimes people cooperate? Well, this is if we have repeated games, right? So you can kind of think about it. If we're repeating this game, then I know that as soon as you break the agreement, right, then we're not going to cooperate in any of the subsequent rounds because I'm never going to trust you again. So there's kind of these tit for tat strategies, excuse me, where as soon as you break the agreement, I'm no longer going to trust you. So I'll try to kind of model this a little bit. Here we go. So let's think about it like, oops, here we've got person 1, and now person 2. These could be firms as well, right? So maybe it makes more sense to think about these as firms, actually, just for the context of this example, right? So let's say I don't break the agreement, or we break the agreement, right? So in the short run, if I ever choose to not break the agreement, or sorry, if we're both not breaking, maybe we're earning like choose $50 million in profits here. Now, if I break the agreement 1 year, maybe I can gain an additional 5 million. So if this was just a game being played one time, my profits here would be what? If the firm 2 breaks the agreement, they get 55. So their strategy choice is always going to be to break that agreement. However, if we both break the agreement, we don't act like a monopolist, and everything gets driven down to that perfectly competitive profit level of 0. Well, I know that if I break the agreement today, the long run payoffs will be that I gain 5 million today, but let's say for the next 20 years, I'm going to lose out on $50 million of profits, right? So this wouldn't be a positive, this would be negative. Well, here then the payoff would be what? I'm doing math in my head correct, right? Because that would be what, 1,000 minus 5 million. So for firm one, they break that agreement. Yeah, they can make $5 million extra this year, but the rest of the time they're making nothing, right? So, oh, and actually, I should technically they were making 55, right? So this should be 945. And then firm two didn't break the agreement, but once the other firm does, they never trust them again. So maybe this next, they only make, say, maybe 40 million, but they're going to lose out on that $1,000, right? So they're at like what, negative 960. And then the kind of same, let's just do same payoffs up here, but kind of flipped. Well, now you can see if we play this game over and over again, not only am I making 50 million, this would be 50 million times what, 20? So if this is like my long run game, what is it optimal for me to do? Well, if firm two doesn't break the agreement, firm one should also not break it forever. Much higher profits. But what if firm two breaks the agreement? I should also choose to break the agreement. Firm one, we kind of have here, what should I choose to do? Well, I would not break the agreement. Here, I would break the agreement. So this is a weird one where we actually have two equilibria, right? If we can somehow end up in this point where we're both trusting each other, not breaking the agreement, we can continue to earn this large amount of profits over the next 20 years. Now, it's also an equilibrium that if either of us chooses to break the agreement, both of us will break it for the rest of time. So which one are we going to end up on? It's hard to say, right? So there are games where we have multiple equilibrium. In fact, we'll talk about some that are a little bit different than this in here in just a second. But this would be somewhat of like a model that suggests that maybe we can see that one of the equilibriums is firms cooperate and don't break their agreements that they kind of agree to. Okay. So let's look at a different kind of model where maybe we have slightly different equilibrium. So let's say I've got a research and development or R&D. One firm, if they put money into R&D, receives 10 million. If both firms kind of put money into R&D, they get 15, right? They like come up with this new invention, this new good, or maybe it's even lowering costs, right? However, they had to put a bunch of money into research and development in order to get this new product. So we kind of think about this as what we call a chicken game, right? So here, if I think about what are Toyota's best responses, well, if Ford is choosing to put money into research and development, what they, or both these firms are, they're both going to be paying, what did I say? 10 million or 9 million. But if they both put money into research and development, we have these new products, we each get an additional 15. So the additional, 15 million, cost of 9, I'd be not 6 million better off. Now, Ford puts money into R&D, but I don't as Toyota. Whoops. Sorry. That new technology is now out there. It's not as much as before because there's only one of us putting money into R&D. So there's 10 million, but I didn't spend any money on research and development. I just mimic what the other company is doing. So now my payoff's 10 million. Same kind of incentives exist on the other side. Now, if we both don't put any money into R&D, we have no costs, but there's also no new products. So what are going to be the best responses? Well, so Toyota, if Ford's putting money into research and development, 10 is greater than 6, and 1 is greater than 0. For Ford, if Toyota is putting money into research and development, 10 is greater than 6, and 1 is greater than 0. So here's another one where we have two equilibriums. And the reason why we call this a chicken game is because what are both of these equilibriums? One of the firms invests in R&D and one doesn't. Now, this is kind of good, right? In the sense that we know at least one of them is going to be putting money into research and development, it's not a prisoner's dilemma because there's no other combination where both people are better off, right? This combination of strategies where they're both putting money into research and development is going to make one of them worse off. So we don't have a prisoner's dilemma. However, for society, where would we want to be? Well, we want all companies to be putting money into new research and development, get all of these new products. It's just that the incentives for the firms don't push us to that point, right? So we end up with this kind of chicken game where we're kind of like, well, we know that if neither of us put any money in, we're going to be worse off. So am I going to be the one that puts money into research and development first, or are you? So we kind of have these complicated games, and we don't have a solution to them in this class. We just want to know that they exist. Okay. So another kind of classic chicken game, just to kind of go through. This is kind of a dumb example, but I don't know. You can kind of see we can do economic examples. You can also just do game theory and everyday decision making. So let's say here I've got rock, paper, scissors. I could go through. This is an example where I have more than 2 strategies, so I'm not going to give you any of these on the exam. But you could actually look at things where you have like 50 strategy choices from each player. So if player 2 chooses rock, the kind of classic game of rock, paper, scissors, rock and rock, there's like a up, no one wins. But if I throw paper and you throw rock, I win, you lose. If I throw scissors and you throw rock, I lose, you win. So we could go through for every single decision. If player 1 throws rock, what should player 2 do? Well, 1 is the highest, so paper. Player 2 chooses paper, what should player 2? Sorry, player 1 chooses paper, what should player 2 do? Well, 1 is the highest, so they should throw scissors. If player 1 chooses scissors, what should player 2 do? They should choose rock. So we could go find kind of player 2's. Oh, I did player 1 first, sorry. There's player 2's best responses. The same kind of thing would happen for player 1, right? If player 2 chooses to throw rock, what should player 1 do? 1 is the highest. Player 2 chooses paper, 1 is the highest. Scissors, 1 is the highest. So where's our equilibrium? There isn't one, right? Sometimes there will be examples where we have multiple equilibrium. There's also going to be examples where we have no equilibrium, right? Okay, so it kind of makes sense in the game of rock, paper, scissors. If you could change your strategy choice, you can always beat the other player, right? So there's never going to be a time where we're both best responding to what the other person is doing if we want to win the game, okay? So when we have no equilibrium, it's basically a guessing game, right? About what strategy choice is going to provide us with the highest payoffs. Okay, and I might give you an example where there is no equilibrium. We don't have any solutions to it yet. There's some things we've got to dive into. In fact, there's whole courses that are on game theory. But for us, we just want to be able to identify these equilibriums, sometimes know that they don't. Sometimes there just isn't an equilibrium that exists. Okay? So the next kind of thing we're going to talk about is not our normal form games, where we're really thinking about people making decisions at the same time, so simultaneously. With extensive form games, we're going to have decisions being made sequentially. Right, so this would be like a not very fun game would be rock, paper, scissors. If the other person has to make their choice first, and then you get to make your choice second, you can always beat them. But there's going to be some that are a little more interesting when we have these sequential decision making. So the way we're going to solve these is what we call backward induction. And I think this will make a little more sense once we actually work through some of these examples. But we're going to depict them not using kind of this normal form matrix, but what we call a decision tree. Okay. So the way that we're going to do these decision trees is we're going to put the person making the first choice at the top. So kind of, I don't know if this might be a really dumb example if you've never seen kind of the old cartoon Charlie Brown, but kind of the running gag is that like Lucy sets up this football, Charlie Brown goes to try to kick it, and she always pulls it away. So what's the equilibrium of that going to always be? Well, Charlie Brown, if he's making the decision first, right, he can either not run towards the, not run towards the football and nothing happens. No one's, he doesn't fall or, doesn't get embarrassed, and she doesn't get the joy out of making him look like an idiot, right? Basically. If he accepts this and starts to run towards the ball to kick it, well, now Lucy has the next decision to make, which is, do I let him kick the ball or do I pull it away? If I let him kick the ball, he gets to kick the football. He gets a positive payoff. But I'm not amused, right? I guess my payoff here is either 0 or you can think of it as almost like negative. If I pull the football away at the last minute, he falls down, negative payoff for him, but I'm amused. I think that this is hilarious. So we always start out determining the best response of the person who's making the decision second or last. So if Lucy is making the decision second, what gives her a higher payoff? Well, if she lets him kick the ball, she's not amused. If she does let him kick it, she's amused. So she's going to choose to pull the football away. Charlie Brown should ahead of time know, okay, well, I know that Lucy, the incentives that exist for her will always be that she pulls that football away. So my decision, I know if I accept this challenge and try to go run and kick this ball, I know that this payoff down here that I'm going to be able to actually kick it and look cool never is going to happen because Lucy's never going to choose to do this. So I know if I choose to accept and try to run towards this football, it's always going to get pulled away and I'm always going to have this negative payoff, which is worse than if I just do nothing. So it should be that our kind of equilibrium is that Lucy will always choose to pull the football away, but Charlie Brown should always reject that offer. Now, the whole part of the, stupid cartoon is that he doesn't understand game theory, basically, and he always tries to run and kick the football and always ends up with a negative payoff. He's not making an optimal decision. Okay. So what might make, be a little bit more of an interesting example here. So I'm going to actually just write this one out for us because I think I don't know. I think seeing me work through this makes more sense. So let's say I've got this current monopoly, right? A firm that is acting like a monopolist. So they can set the monopoly price or they can set a perfectly competitive price. Right? We then have someone who's thinking about entering this market. And, maybe this isn't the perfectly competitive price, but it's a more competitive price. Right? I think here I set up as the extreme. And if we understand the extreme, we can understand, okay, maybe it's not quite perfectly competitive, but the same kind of principles would apply. So the new entrant has a decision. Do I enter or stay out of this market, right? Given the price that current monopolist has set. Well, if the current monopolist sets that higher monopoly price, this new firm enters, right? Well, the new entrant can kind of undercut that price, right? So my monopoly profits will actually be negative. Everyone's going to buy from the new entrant who selling at a lower price than the current price I'm setting can earn positive profits. Now, if the new entrant decides to stay out, well, here I'm going to shorthand my monopoly profits. We said are always positive. And if I stayed out, the kind of, I guess here I could probably put like the new entrant, right? Their profits are zero. They didn't do anything. They didn't enter this market. Now, if I set a lower competitive price and this other firm enters, right? Well, now we're both setting a lower price. Maybe there's not enough profits, right, to go around so that we end up with the profits of both firms are now negative. Right? Now, if they set the perfectly competitive price, the monopolist will earn profits of zero. If the new entrant stays out, they're earning profits of zero. So what should that we'll start out backward induction, right? What should the new entrant do under both scenarios? Well, if the monopolist sets a perfectly competitive price, if I enter that market, I know that there's no profits to be had there. If I enter, it's going to be a higher quantity. It's going to push the price even lower. My profits will be negative. If I stay out, my profits are positive. So, or sorry, not positive, are zero. Zero is better than a negative value. Now, if the monopolist sets a higher monopoly price and I enter that market charging a lower price than that, well, now my profits will be positive. Whereas if I stay out, they're only zero. So we've got the best response or the best decision of that person making the decision second identified. Now, knowing that, the monopolist says, okay, if I set this perfectly competitive price, I know that this new entrant will always choose to stay out of this market. My profits will be zero. So I don't even really have to consider these because I know this can't happen. Now, if I set a monopoly price, I know the new entrant will always choose to enter. I'll be earning negative profits, right? So I shouldn't even consider this because I know that if I set the monopoly price, the new entrant will always choose to enter and undercut my price, earn positive profits. So for the monopolist, if I choose this higher price and this firm enters, my profits are negative. If I set a more competitive price and keep them out, I get zero. What's better? Zero is better than a negative value. Now, it could be like these are slightly above zero, right? So that you're still getting that, maybe I don't set the perfect competitive price, but maybe I set it such that like, it's really close. And so that other firm, they're not going to really be able to earn any profits, hardly any profits, or they would still be negative if they entered. So the same kind of principles would apply. Here, I just kind of chose the extremes of a monopoly and a perfectly competitive price. So why is this a good thing? Well, if we had sequential decision making, it's going to push us towards this equilibrium where the monopolist is setting not the monopoly price, but a more competitive price in order to keep other firms out. So if we didn't have any barriers to entry, we actually see that we could have a monopolist, but they still behave a little bit more like a perfectly competitive firm if we have the threat of entry and exit of other firms. Okay. So that's how we solve these sequential models or these backward induction models, right? You do the same thing with that rock, paper, scissors example. It's not very interesting because you can kind of see here, well, what would player two's best response be? One is the highest, one is the highest, one is the highest. So if I'm from one, well, if I throw rock, player two is always going to throw paper, I'm going to lose. If I throw paper, they're always going to choose scissors, I'm always going to lose. If I choose scissors, they're always going to throw rock. So here, I'm indifferent. I don't care what. If I have to be the one that makes my decision first in this rock, paper, scissors game, I'm always going to lose. So we can actually have multiple equilibrium in these sequential game models as well. Right? Excuse me. So I have another example that you kind of think through. So I have this sharing example. So let's say you've got $100 and you're told you can share it with a friend. Right? You can divide it up into $1 increments. If your friend accepts the offer, you both get nothing. If your friend rejects the offer, you both get nothing. If your friend accepts the offer, he gets to keep the amount you offered him, and you get to keep the rest. Right? So what is that going to look like? So we're going to kind of try to model this as an extensive form game. So we'll just start out thinking about kind of the first decision, right? So we've got person one who's making the offer. So the very first thing they could choose to do is what? Give nothing, right? Excuse me. In which case, person two has a decision to make. They can accept or reject that, right? So if they accepted it, person one gets to keep all $100. Person two gets nothing. If they reject it, well, we both get zero, right? Okay, what's the other choice I can make? What if I just offered them $1? Well, now person two has those same decisions. They can either accept or reject. Right? So here I've offered them $1. So if they accept it, they get $1. I get to keep 99. If they reject it, we both get 0. Right? And then I'll just do one more. Let's say I offer them $2. Person two can either, I'm going to shorthand this, accept or reject. Here, I would get to keep 98. They keep the 2 I offered them. If they reject it, we both get nothing. So where's this equilibrium going to be? Well, we'll solve it backward induction. Person two makes the decision second, whether or not to accept or reject. So if they're offered nothing, I'm indifferent, right? If I'm offered $1, I know I'm going to accept that, right? Because $1 is better than nothing. If I offer them 2, I always know they're going to accept that. And then that logic would go all the way down the line, right? So now as person one, if I offer them 0, here it's kind of tricky, right? I wouldn't give you one probably this difficult on the exam or anything like that. In fact, the ones we worked through in Top Hat will have a clear-cut answer. But here, the person is indifferent about accepting or rejecting my offer. So my payoff could be 100, could be 0, right? Now, if let's just say the person two doesn't really care. They just make their choice random because the payoff is the same either way. We would do like an expected value thing. So here, the expected value would be what, 50? Now, I'm not going to make you do expected values, but just to kind of give you like a more realistic view of this. And then I'm going to change it to make it a little bit easier, I think. So if I offer them 1, I know that they're going to always accept it, right? Here, I don't know, right? I could accept it, could reject it, could end up with 100, could end up with a 0. Here, I know if I offer them even $1, I'm guaranteed they're going to accept it and I'm going to get 99, which is if I offer them 2, they're always going to accept it and I only get 98. So what's better? 99. So if this was our sharing model, this would predict that in order to avoid this scenario where maybe I get nothing, person 1 would always at least offer the other person $1, but there's no incentive to offer them anything more than that. Because I know if I offer you $1, you're better off if you accept it than if you reject it. So why would I offer you 2? Because I know you're better off there as well, and I'm just having a lower payoff. So there, our equilibrium would be that the person 1 offers $1, person 2 accepts it. Okay. Now, what might be a more realistic view of this? So if you had this scenario play out and you knew the other person was given this choice of like, you can offer this other person increments of $1, right? So you could choose 0, you could choose 1, you could choose 2, right? And then, after you do that, person 2 gets to make this choice, which is they can accept or reject the offer. So I'm going to change this a little bit because if someone did that to you and they offered you $1 and they have 100 to offer you, it could be any value. What might you do? Just reject it out of spite, right? So probably what ends up happening is the payoffs actually look a little bit different, right? Because it's not that if I reject the offer or I accept the offer, I get nothing, right? If I reject the offer here, maybe it like brings me joy because I know this person was so greedy that if they offered me 0 and I accepted it, they get to keep 100 and I got nothing. That makes me so mad that I know that if I reject that offer, they get nothing. That actually is going to bring me some joy. Same kind of thing here. Well, if they offered me $1 and I accept it, it's 99 and 1. But even that, I get a benefit of 10 out of the fact that I just reject these low offers. So here, even though I'm getting to keep $1, rejecting it because they offer me such a low amount still would provide me with some positive level of kind of utility. And same kind of idea here. If I accept, I get to keep 2, they keep 98. If I reject, they keep nothing. And I don't get to keep the $2, or sorry, I shouldn't do this here. This was supposed to be 10 because we don't get to keep the $1 here, right? But I'm getting this value of like spite, right? Well, so now notice if we try to solve this for person 2, for these really low amounts, it's always better to reject the offer because keeping $1 or $2, it brings me more joy that the other person got to keep nothing because they offer me such a small amount. So person 1 looks at this and says, well, I'm going to get nothing, right? I know that person 2 was always going to reject for these lower amounts. So I don't really care which of these I offer. Now, eventually, what's going to happen though, and I'm not going to do every single increment, but just to kind of give, so let's say I offer to person 2 and they can accept or reject. We can kind of keep going these possibilities. Let's say I offered them $11, right? Well, now if I reject this, right, it kind of brings me some joy that this person still is kind of offering me a low amount. They get to keep nothing. But if I accept it, I know that they'll get to keep 89 and I'll get to keep 11. So what would person 2 choose to do here? Well, as soon as it gets to this point where the amount offered is greater than how much joy it brings them to see the other person that isn't really treating them fairly, what would be fair, 50-50 split, there will be a point where they're like, okay, yeah, I'd like to see the other person not get to keep this $89, but $11 is a high enough amount where I don't value my spite that much. So in practice, what we see is like, yeah, it's not that I just get to keep nothing, right? I get no benefit from rejecting. I probably get some benefit from rejecting these offers that I feel like aren't fair. So they've run these experiments in the lab, and I can't remember, I should have looked this up before I recorded the video. I can't remember the exact value, but there is like a cutoff that they find that people, if you offer them like below, like they know you kind of have the power. And if you offer them anything like that below like a 30% split, they're just going to reject it because the spite is more beneficial than the amount that you're offering them. As soon as you get somewhere above, like I said, I think it's about a 30%, 20, 30%, there they feel like, okay, well, you were in kind of the driver's seat. I wouldn't have offered, a 50-50 split either. And so then maybe I'll accept some of these lower amounts, but not the extremely low amounts. Okay. So I don't know, kind of just thinking about how we would solve these extensive form models. Hopefully we can kind of see how they might have application not only to markets, but also just like individual decision making. Okay. All right. So I have a couple that I want to go through as well. So I need to have this so I can actually see it. I'm going to write them out as opposed to kind of go through them on Top Hat. So these are the other Top Hat questions I had. So the first one is going to be one of these extensive form games. So I've got, maybe it makes sense to do it this way. Firm one, and they're either going to choose to invest or not invest into research and development. Firm two is going to see firm one's choice, and they get to make their choice second, right? So here, they're going to either choose to invest or not invest. So I think when we had this set up as a normal form game, we had an equilibrium for that research and development example where it was a chicken game. We ended up with two equilibriums, and it was going to be that one company invested, one of them didn't. Oops, sorry for the glitch there. And I think I bumped my camera. So the payoffs we had were 50 million, negative 20 million, 60, 60, negative 20. These are all millions. And then 10 and 10. So the way we would solve this is think about who's making the firm decision second, firm two. So if firm one chooses to invest, what will firm two do? Well, if they invest, they get 50 million. Once again, player one's payoffs we always put on the left, player two on the right. So which one of these is higher? Not investing, right? I can enjoy the benefits of this research and development that firm one had without having all of the additional costs. Now, if firm one doesn't invest, and I don't, and I invest, I get negative 20. If I don't invest, I get 10 million. So what's better? Not investing. So we know firm two's going to have this dominant strategy, regardless of what firm one does, which is to not invest. Now, knowing this, firm one says, okay, if I choose not to invest, I always know this is going to be the outcome. So I only have to consider this. Invest, oops, went too far. This is always going to be the outcome. So I shouldn't even consider this as an option. So if I choose to invest, I know firm two would always not invest, and I'll end up with negative 20. If I choose to not invest, I know firm two will always choose not to invest as well. I'll end up with 10. Which of these is greater? 10. So what do we end up with? Not a chicken game, but if we have these decisions made sequentially, we actually end up with neither firm putting any money into research and development, right? Which not great for society, right? So here's kind of a I don't know, an interesting example I kind of had set up. I was going to like to do this in class, but I just want to talk through it. So this is our sequential game. We end up with one equilibrium here. This will probably be a little bit more like the types of questions, since it's a little more firm related to these oligopolies you would see on the exam or a quiz. So the other example I had in the top it was, let's assume that, and this is where it gets a little bit more complicated, but we could somewhat model this as a simultaneous equation game. So let's say I had everyone in the class guess a number, right? Somewhere between 0 and 100, and the person who can guess half of the class average is going to win the game. And I had everybody guess. We calculate the average, and then whoever has half of that average as their guess would win. So the thought would be, okay, if everyone just completely randomly guesses between 0 and 100, what would the average be? Well, the average there would be, what, 50? But remember, to win this game, I need to guess half of the average. So what am I going to guess? Well, I would kind of guess 25. But I know that everybody else also knows this rule. So everyone else is going to try to also guess 25. Well, if everyone guesses 25 and the average is 25, what should my new guess be to win the game? 12.5. But I know that everybody knows that. So if everyone guesses 12.5, I'm going to guess what? Half of that. So what? 6.25. And this kind of continues all the way down to what should we actually all be guessing? 0, right? Now, will everybody be able to think this far down? No. So once again, they run these in these experimental economic experiment labs. And what they call this is like some people only kind of originally think of this. They say, oh, well, everyone, if it's random, everyone's going to guess 50. I should guess half of that. And we call that like a level 1 thinker. Well, a level 2 thinker would say, well, I know that everyone's going to try to guess half of like a random average, so I should be guessing half of that. That would be a level 2 thinker. And then, okay, yeah, but if everyone knows that I should be guessing half of this kind of random average, but if everyone does that, I should be guessing half of that. And that if everyone knows that, then I should really be guessing half of that. That would be kind of our level 3 thinker. And we kind of continue all the way down. And kind of the more broad term that we call this is there's different types of thinkers. People think through things a further level, right? And we have level K thinkers, right? So level 1, 2, 3, etc. So questions like this, like where exactly in a class of 300, it'd be kind of cool to actually do this. And maybe I'll try to do this when we kind of meet again after Thanksgiving break, kind of run this to kind of see, well, where does the average actually end up? How close is it to 0? How many level 1 thinkers are there in our class? Well, I guess if you watch these videos, it should be that those guesses are really close to 0. Anyways, so that kind of wraps it up for module 12, oligopoly models. We'll pick up after Thanksgiving break looking at monopolistically competitive or monopolistic competition models.